Welcome to the 16th session of galvanic cells, which comes again under electrochemistry, and again in this session we will be continuing with the corrosion of metals, and this is the second part of it. In this session, we will be dealing with the electrochemical theory of corrosion and what are the methods used to prevent corrosion. So, corrosion is also very important, only then you can save the metal. So, let us go in detail. First one, we will see the electrochemical theory of corrosion. As I have mentioned in the previous class, the corrosion is due to the formation of anodic and the cathodic areas where the anodic process occurs and the cathodic process occurs. Now, according to electrochemical theory, it says that corrosion is an electrochemical process involving anodic and cathodic processes. That is, there will be an oxidation, and in combination with this oxidation, there will be a reduction also occurring. The special characteristic of most corrosion processes is that oxidation and reduction steps occur at two separate locations of a metal, and this is because metals are conductors and they can easily allow the flow of electrons through them. Okay. So, the anodic and cathodic regions, you can pass the electrons through the metal itself, because metal conducts electrons, they are conductors. The presence of a thin film of adsorbed moisture is enough to transport the ions to and from the metal surface. So, a small amount of moisture, that itself will help to transport the ions. So, these are the conditions how a metal is getting corroded. We will see in detail the rusting of iron, the electrochemical process. So, rusting of iron is one of the example. During rusting of iron, electrochemical cells are formed on the surface of the metal in the presence of oxygen and water, which contains dissolved oxygen. And dissolved oxygen, when oxygen and as well as, that is, oxygen is coming from air, dissolved carbon dioxide which is within the water, it reacts with carbon dioxide and it forms carbonic acid, which acts as the electrolytic solution, and that will be the electrolytic solution where we can transfer the ions. So, ions move through electrolytic solutions while electrons move through the metal. Okay. Now, at one spot of iron object, if you are having an iron object, one spot of the iron occurs the oxidation and that spot behaves as the anode. Okay, there oxidation takes place and that spot will be the anode. Now, some other spot in the metal, anywhere in the metal, where you can have oxygen should be present at that region available, and H plus ions also should be present, and that is available from dissociation of carbonic acid, the H plus ions. Okay. At that spot, or you can have any spot in the metal which is capable of taking electrons, that itself is enough, but in the case of iron, it is the oxygen in the presence of H plus ions which acts as a region where reduction occurs and it acts as the cathode. Okay. So, that will be the spot which acts as a cathode. Now, where are these regions which is susceptible to form corrosion? Now, we can see that during a production of a metal object, there will be during its formation and machining, all these regions, like if an iron piece is welded, again it is extruded. So, it undergoes some type of forming, that is some abrasion over the surface areas. These areas, what happens is, there the ions will be at high free energy, they will be having a higher free energy, and therefore, if they have got higher free energy, they have a tendency to react and lower their free energy, and therefore, those are the regions which become more anodic. Okay. So, that is a region where the corrosion is going to start. In contrast to anodic sites, cathodic sites can be anywhere where you can have the use of these electrons released from the anode. They consume, the cathodic region is consuming the electron on the surface from where it has been released and transported. So, it is not that localized, it can be anywhere on the surface of the metal. The cathodic process can occur anywhere because metallic oxides are usually semiconductors which do not inhibit the flow of electrons. Okay, so, it can be anywhere, though in case of iron, it is the exposed region to oxygen acts as the cathode. It is very important, there should be availability of oxygen. Now, let us see what are the electrode reactions that occurs during the rusting of iron. These are the electrode reactions. The anodic region, the iron gets oxidized to ferrous Fe2 plus state and releases the electron. This is of course an oxidation process. Now, these are the region where the metallic iron has got higher free energy, and therefore, they get oxidized as Fe2 plus. Cathodic region is a region, I told you, it is very important, the case of iron, there should be availability of oxygen, and this oxygen in the presence of H plus ion takes up electrons and gets converted into water. Okay. So, this is the cathodic reaction, and this region acts as the electron acceptor region, and in anodic regions the electrons are being released. Okay. Now, the overall reaction you can write it as iron solid combines with oxygen in the presence of H plus ions to get oxidized to Fe2 plus. Okay. The reaction does not stop there. Now, what happens is this Fe2 plus further reacts with water and oxygen to form the ferric oxide, that is iron in the plus 3 state. Okay, this is in the plus 2 state. From there it oxidizes to the plus 3 state, releasing H plus ions, and this ferric oxide then combines with water molecules to form a precipitate brown colored residue known as rust. That is what we see on the surface of the iron, and this rust does not stick on to the iron surface firmly, it does not adhere firmly, and therefore, what happens is the rust comes out or peels out and the fresh iron surface is exposed. Now, here there is a picture showing this is the anodic site. At anodic site, that is iron gets oxidized to Fe2 plus, releasing electrons. That is what we have seen in this reaction. Okay. And here we have oxygen taking up the electrons with H plus ions. In the presence of H plus ions, it takes up electrons and gets it is not balanced, I am showing it because this is not that clear. So, it gets converted into water. Okay. This is where electrons are consumed. So, this becomes the cathodic region, and this is the anodic region where the electrons are released, and the ferrous ion gets oxidized to ferric, and this forming ferric oxide. This ferric oxide combines with water to form the rust Fe2O3XH2O, that is the rust, that is the brown color residue we see on the surface of the iron when it gets rusted. Okay. Now, what are the methods to prevent corrosion, because metal is getting destroyed, especially the main loss is for the iron materials. Okay. So, first one is the barrier protection. Barrier itself shows that there should be something to prevent the direct contact. Okay. Barrier protection works by providing a barrier of corrosion resistant material and the damaging environment. Okay. So, we have a barrier. If you have a metal, you have another barrier, so that the metal is not directly in contact with the damaging environment. Okay. So, the metal surface is protected from direct contact with the surroundings by coating it with paints, certain oils, enamels, or some thin protective layer of corrosion resistant metal, that is usually electroplating what we do. Okay. All these metals can prevent rusting of iron or any metal by barrier protection. Example, rusting of iron can be prevented by painting iron articles, that is what we do commonly, or plating them with more corrosion resistant metals like copper or nickel. So, they can be plated over iron to prevent the corrosion of iron, that is one method. Next one is sacrificial protection. From the name itself, we know that there is something has been sacrificed to protect the metal. The corrosion of a metal can be prevented by covering it with a surface of a layer of a more active metal like zinc, magnesium or aluminum. The other case, we have been corrosion resistant metals like copper or nickel, they do not react fast. So, such metals are being coated. Here the case is different, we are going to coat the metal surface with more reactive metal, so that the metal will be prevented and the highly reactive metal, it gets corroded and the other metal is saved. Okay. The prevention of corrosion of iron by coating it with more active metal is one of the example. Okay. Here we are going to take the case when iron is coated with zinc. Okay. The more active metal acts as the anode. Now, what happens is the more active metal, let it be zinc or magnesium or whatever it is, that coating acts as the anode, it gets oxidized. Now, the electrons, they remain in the metal, that is they are transported to, if it is iron, to that metal iron. Now, this ion, since the electrons are getting accumulated, it cannot get oxidized as long as this protective coating is there. Okay. So, what is happening? Because of this active metal, a negative polarity is being induced at the metal below it, because active metal gets oxidized and pumps its electron to the metal, and therefore, the metal becomes negatively charged, which prevents its further oxidation. Now, what happens is, in the case of iron, okay, more active metal acts as a anode. It can be either zinc, magnesium or aluminum. Iron acts as a cathode, it can only undergo reduction, that is the possibility is it can accept only electrons, but not get oxidized. Okay. And what happens is, the more active metal keeps on losing its electrons and goes into the ionic state, thereby preventing the loss of electrons from iron, or in short the corrosion of iron is prevented. Okay. The process of covering iron articles with a thin layer of zinc is known as galvanizing. You have heard of galvanized pipes, galvanized nails, all these things, that is nothing but iron being coated with a layer of zinc, which is more active than iron. Now, here that is a sacrificial coating, this is a coating of zinc. Okay. As long as this coating is there, the iron is protected because zinc will get oxidized, pushing its electron to iron. Okay. So, iron is saved, it is not undergoing any corrosion, and therefore, it is a sacrifice from the part of zinc, because zinc is getting corroded instead of iron, and iron is saved, and therefore, the word sacrificial coating. Okay. Now, what happens if an iron is coated with less active metal, especially tin? You might have seen eatables coming in tins, milk powders in tins, chocolate powders in tins, all those are coated with it is actually made of iron, that container is made of iron with a coating of tin metal inside it. You can see that it will be highly glossy in the beginning, and after some time you can see that it gets corroded easily. So, here the iron tin is coated with an less active metal tin, it is a metal tin. Okay. The iron, anything, cans or any article coated with tin metal. Okay. This can accelerate rusting. Now, how? Once there is a small scratch or a bit of space where iron is exposed, just imagine. Now, tin is not that active. Once it is exposed, iron gets oxidized as Fe2 plus or ferrous iron. These electrons will be taken up by tin easily, because tin does not like to get oxidized. So, tin gets reduced. Now, since tin takes up electrons, iron provides electrons again and again, and more of iron gets rusted. Okay. So, what is happening here? It is accelerating the rusting of iron, because tin is a passive metal which has been coated over iron. As long as the tin coating is intact, everything is okay, there will not be any rusting. If there is a small pinpoint destruction of tin coating, rusting takes place, and it occurs at a very high rate, and in a few days you can see that the whole thing is rusted. Okay. So, that is the picture here. See, once the tin coating is broken, iron gets oxidized, and what happens is the tin takes up the electron, and this occurs at a very high rate, because tin is ready to accept electrons. Okay. Next type is electrical protection. In electrical protection, we have two types, cathodic protection and anodic protection. And in cathodic protection, we have two types of cathodic protection. One is the ordinary cathodic protection, and the other one is impressed cathodic protection. Okay. So, first we will see what is cathodic protection. Cathodic protection, it means from the name itself, the metal to be protected is maintained as a cathode throughout the time, so as to prevent the oxidation of the metal and the corrosion of the metal. So, to prevent the metal being getting corroded or getting oxidized and then corroded, you can prevent it by maintaining that metal as a cathode. Okay. So, what happens in this process is, we have in this ordinary cathodic protection, we have an more active metal connected through a wire or directly through an electrolyte or whatever it is to the metal to be protected. And this method is usually done for protecting underground iron tanks and big iron pipes which carry some fluids and all these things. And these iron tanks or iron structures, they are connected to more active aluminum, magnesium or zinc plates. Okay. Now, there is a picture over here. So, this is magnesium, inserted below the ground. This is the top portion where they have shown the grass, and under the soil we have this pipe. This is iron pipe they have shown, any iron tanks or whatever it is. So, this is magnesium, which is more electropositive. In the electropositive series, you can see that magnesium is more electropositive than iron, and once these two are connected through a wire, see, this is a wire used to connect. Now, what happens is magnesium undergoes oxidation in preference to iron. So, when magnesium gets oxidized, it pumps its electron to the iron. So, iron is made cathode because iron accepts electron and magnesium. So, magnesium is acting as the anode and iron is acting as the cathode. Now, since there is an electron density at iron surface or in the iron metal, it is incapable of getting oxidized, and therefore, what is happening? This is made cathode and iron material is protected. Now, what happens here is magnesium gets converted into ions and goes into solution, and the soil and the water content acts as the electrolyte, which facilitates the movement of ions. Now, this method, though it is, as long as magnesium is there, iron is protected. So, once it is connected to a magnesium piece or rod, till magnesium is present, iron rods are, or iron pipes or structures, they are protected because it is made cathode. Now, this method has got a very big drawback. This metal, that is, if it is magnesium, magnesium will be releasing its magnesium ions into the soil, and therefore, the soil get polluted with metal ions, and also along with soil the water also gets polluted if it is soluble in water. Another drawback is the anode gets consumed because anode is reacting, okay, and this anode, this is being converted into ions and it gets consumed. Once it is consumed, if you have to protect the structure, you will have to replace the anode. So, that is another drawback, the anode has to be replaced. Now, this has been overcome by another new technique known as impressed current cathodic protection. Now, impressed current means we are going to supply a DC power and then we are going to make the metal cathodic. It is given a cathodic potential, and to keep the metal cathodic protection, we will have to use another anode also. Anode will be usually any material like graphite, it can be either mixed oxide or platinum coated titanium or niobium. So, these are the materials, they are used as anode, and these anode is connected through a electric power DC source to the metal that has to be retained as the cathode. So, here we have the picture of that. Here this is the structure that has to be protected. Okay. This structure is connected to a DC source, okay, and you can see that electrons are being here. This is a negative pole, and therefore, the structure will be having an electron rich environment, and this will be the metal which is acting as the positive or the anode. Okay. Now, here the advantage is that since the DC power is supplied, the structure remains negatively charged and this remains positively charged, and therefore, there is no loss of metal, no need of metal getting oxidized. Okay. So, what happens is the structure is protected, no need of replacing the anode or anything. Okay. And this type of protection is actually done for ship hulls, because we know that ship moves in sea water and they are exposed to highly electrolytic solution where it enhances the corrosion, and therefore, such ship hulls as well as the structures for oil refineries and all those things under sea, we do this method to protect the structures, impressed current cathodic protection. Okay. Here the difference is we are giving a DC current and making the structure cathode and protecting it. So, here the structure is protected, making it a cathode. Remember, because we are going for another type also. So, here the structure is maintained cathode by applying DC current, and therefore, it is known as impressed current cathodic protection. Next is anodic protection. Anodic protection, it is similar to cathodic protection, that is impressed current cathodic protection, in which here we are supplying a DC power and protecting the structure or the metal to be protected as the anode. In the other case, it was the structure was maintained as the cathode to protect it. In this case, we will be protecting it by making it anode. Okay. Now, so anodic protection is, we have an impressed anodic current on the structure to be protected. Remember, we are having an anode, it is made as an anode. Now, what happens during this process? The structure gets polarizes to its passive region. That is also an important factor, because only those metals which when given an anodic current move to a region where it behaves as a passive metal. So, that is the region to which we move the potential of the metal to make it passive. Only if it is made passive, it will not corrode. So, that is what happens here, and that potential has to be maintained. We have to strictly maintain that potential. If the potential is varied, there may be corrosion occurring. So, usually in these processes, the impressed anodic current is applied to structure using a potentiostat. You can say it is a potentiostatic current we will be providing. The potentiostat keeps the potential difference constant at that particular region, and it is constantly monitored. Once it changes, we have to adjust it, and the potentiostat keeps it fixed in that potential, that is, the metal remains in the passive region. So, it is the impressed anodic current to the structure to be protected by polarizing it to its passive region and maintaining it there. For metals that exhibit passivity like stainless steel, nickel alloys, titanium, etc., a small passive current over the wide range of potential is applied, and this is done for all structures where we have very aggressive environments like their exposure to sulfuric acid, phosphoric acid or aqueous ammonia. So, in such cases there will be metallic tanks or anything else like made of stainless steel or anything, there all these has to be protected by giving them an anodic protection. Okay. So, that the metal remains passive and there is no interaction between the acid or ammonia with the metal. Okay. That is anodic protection. Next is, this is common type, that is use of anti-rust solutions, that is alkaline phosphates and chromates are used as anti-rust solutions, especially in the case of iron. The fresh iron is coated with alkaline phosphates or chromates. Chromates are a bit more costly. It is usually alkaline phosphates we use it, and the iron parts are covered with it. These coatings, they prevent the availability of H plus ions, so that corrosion cannot take place. Besides, it forms an insoluble sticky layer of iron phosphate on the surface of iron. It is a sticky layer, it will not peel off like rust. So, two cases are there, it prevents the availability of H plus ions, and second one, it acts as a sticky layer over the iron object and prevents the iron from rusting. It gives a protective coating over the that is use of anti-rust solution. Next one, this is particularly applied, this is for iron. Next method is usually made for mostly for aluminum and aluminum alloys. This process is known as anodizing. Anodizing, again it is an electrolytic passivation process used to increase the thickness of protective oxide layer on the surface of metal parts. You have heard of utensils and also a number of aluminum sheets and all anodized ones. And what are they doing is that there is a protective coating of aluminum. I told you aluminum corrodes to form aluminum oxide, and this aluminum oxide, they act as a thin film on the aluminum metal and protects it from further corrosion. So, that process is being done using an electrochemical method, and therefore, the name anodizing. Here it is an electrolytic passivation process used to increase the thickness of the protective oxide layer on the surface of the metal parts. The process is called anodizing. Why? Because the part to be treated to form its oxide layer is the anode in an electrolytic cell. The part to be protected is kept as an anode in the electrolytic cell, and therefore, the name anodizing is given. And this process is mainly used for commonly even up to date today in our life, we use a number of anodized aluminum vessels and also sheets and many things. Okay. Now, this is we keep the metal in the acid electrolyte bath and an electrical current is passed through the solution, and this metal is kept as the anode. And the bath will be having a cathode attached to it, there will be a cathode, of course, only then the electrical circuit will be complete. Here aluminum which acts as the anode, what will happen? It gets oxidized to aluminum oxide, oxidation. Okay. When current is passed, oxygen forms on the surface of the aluminum, creating a thin film of aluminum oxide, or you can call it as the anodic layer. Now, the quality of anodic layer depends upon the temperature at which the process is carried out, and secondly, the concentration of the electrolytic cell. So, temperature and concentration of the electrolytic cell, and also on the type of electrolyte used, that is usually we use the acids, and type of acids, varying on the type of acids, we have different type of anodizing processes. So, here nothing is occurring, that is aluminum will be kept as the anode, cathode can be any other metal, and during this electrolysis process, when the current is passed, this which acts as a anode, that is the aluminum part or the alloy of aluminum, it gets oxidized to aluminum oxide, forming a coating over that metal. Okay. And this protects aluminum from getting corroded further. Okay. Now, what are the types of anodizing? First one is the chromic acid anodizing. From the name itself, we know that the acid used is a chromic acid. Here, if you need only a thin film of coating, we use chromic acid anodizing, where only a thin film is formed. As long as the film is retained there, the aluminum is protected. Next is sulfuric acid anodizing. Here we have a thicker coating, okay, and this thicker coating when we use sulfuric acid. Now, there is another one, you have seen the hard anodized cookers and utensils nowadays, it is very common, that is hard anodizing. In hard anodizing, we use sulfuric acid itself as acid, but it forms a very thick coating provided the process occurs at a low temperature. At low temperature, the process, the anodizing process occurs slowly, and we have a very thick hard anodized coating on the metal, and that is what is more safe and gives protection to the aluminum as well as the aluminum alloys. Okay. Now, anodization prevents, not only prevents the corrosion of aluminum, it can improve the color absorption capacity on aluminum surface, and therefore, by anodized aluminums you can have in different colors. That is a picture shown here. These are all anodized aluminum which has been colored. See, a wide variety, and the appearance enhance how beautiful it looks. Okay. And since anodization is mainly done for aluminum and its alloys, it can also be done for titanium, zinc, magnesium, etc., but it is not that much in practice. It is mainly used for aluminum and its alloys. Now, let us conclude this session. Like we have been dealing with the electrochemical theory of corrosion, methods to prevent corrosion like barrier protection, sacrificial protection, and electrical protection. In electrical protection, you have seen cathodic protection and anodic protection. In cathodic protection, you have simple cathodic protection and impressed current cathodic protection. Anodic protection, of course, it is the impressed current anodic protection alone. Then another is for anti-rust solution, use of anti-rust, that is mainly for iron, and anodization is mainly for aluminum and its alloys. There we have been seeing chromic acid anodization, sulfuric acid anodization, and hard anodization. So, with that we finish this topic. Thank you.